Okay, I'm going to try to be as loud as I can. I'm not sure that this is recording properly, but I think it is. So I'll let you guys decide that. Maybe when I get back to my office, I'll take a look at it. I don't know that I'll be able to change it, but at least this is a good place to start. This is the next question, basically, where we left off. And I thought I'd look at this and discuss this. I didn't think it was that. I thought it was fairly clear, but I've had some questions, so let's talk about this for a minute. So this is asking from calculus. You know that you guys know the mean value theorem. Suppose that f of x is continuous on the closed interval x1, x2, and differentiable on the open interval between the two. Then there exists an x3 that's between x1 and x2, not including x1 and x2. So it can't be x1, it can't be x2, such that the derivative of that point, or that x value, x3, is equal to basically the middle of f of x squared minus f of x1 over x squared minus x1. Okay, so first, my hope is you understand what that means. And that means that this value, just going to write over here, just going to write, oh, yeah. No. Okay, all right, so this here is the y value for this x, right? I mean, that's all that says. And it's the difference between the y values over the difference between the x values, which is basically telling you that it's the slope, right? Because that is what your slope is. It is the difference over your rise, which would be your y values, from your x, which would be your run. So rise over run. What does this mean geometrically? So geometrically, let's put a little picture here. Chart. Everything is nice and straight. We're going to pretend this will be my x's. This will be my y's, right? These go on forever. Okay. And then let's put a curve in. Let's do a curve in a different color. We'll do that color. So we have a curve. Let's start it down here, maybe. It goes up like that. Okay. All right, so there's my curve. And it really doesn't matter what I draw, but it's a curve and it is continuous. So this is continuous on some intervals. Let's give it some intervals. Let's use this one. This will be x. And then this one, this will be x. Right? I don't care which one's which. You number it however you want to number it, because it doesn't really matter. I mean, it will for the calculation, but that's not really understanding. That's an example. Okay, so that gives us these 2 points. And so there's less confusion between x1 and x2. Let's say this one equals, let's say this one here is going to equal a, and this one's going to equal b. I'm just saving confusion. So that means this point right there, that point is going to be b comma f of b, right? Which that point is right there. That is, without a shadow of a doubt, that point. This point over here, well, this point is going to be, maybe we put it here, a, yeah. Stop it. Stop it. F of a. Right, so that's f of a. We could even label this nicely as a and capital B. just to make things easy. So the geometric interpretation of the mean value theorem. So the geometric interpretation says that there is a point between there that actually is parallel, the tangent of that point is parallel to the chord of AB. So that's really what it's saying. I'll maybe write that in words in a second, but let's figure out what the chord is. So chord between AB is this straight line between A and B. That's a chord between A and B. And it says that there's this X3, but we're going to label X3. What do we want to label X3? Let's put X3 as, let's do a different color. This color maybe, that color is a different color. And we're going to put a point here. And this point will be point P. P is a good choice. P. Why? Because I don't care. Because it doesn't really matter. It's just a point. It's P. And the tangent of that point, let's see if we can draw a tangent here. That's our tangent. Nice and straight. It goes up this way, right through that. Okay, so that tangent, that dashed line, is parallel to the chord of AB. That's really what this whole thing says. So if I was to write it out in words, the picture is a picture. It doesn't answer the question, right? It's just a picture. We're going to use not this color because that don't really matter to me. And geometrically, so let's see, this is A. And I'm going to use shorthand. You guys will have to translate it, but that's fine. Yeah. There exists a continuous curve between AB, A and B, having a unique tangent for all points take this to P, put this to P, this P, a point on the curve where okay, so where P doesn't equal A, because that's not even remotely interesting. Let's see. And P doesn't equal B. Such that the tangent at P is parallel board. Okay. Yeah, that is it in geometric interpretation, right? We're thinking about slope. This is true. And that's the way it goes. Now, you guys will have to, write the whole thing out. I did use a lot of mathematical notation. If you have questions, ask, please. My hope is you'll watch this beforehand and you guys will have some questions if you need them tonight for class next. And then what about the next one? Suppose that f of x is equal to some quadratic with a not equal to 0, because that wouldn't be a quadratic. Show that for any x1 and x2, the unique value of x3 that satisfies the mean value theorem is the midpoint, right? That's what we're showing. We're showing it's the midpoint. So, okay, that should be fairly straightforward. Let me do that in a different color, and we'll see if there's even enough room to get that in here. There might be. So since f of x is continuous, right, justify why I can do this on, and I'm going to use the subscript x1, x2, the closed interval, that I know that, and because f of x is a polynomial, f of x is differentiable on closed interval x1, x2, right? We know enough to say that. Right? And if you don't feel you know enough, say that right off the bat, then you definitely need to practice some stuff on calculus. So from this, we have by by the mean value theorem, right? Mean value theorem. We get that x3 is in between x1 on the open interval, x1, x2. We have that such that f of x3, right? This is just the mean value theorem. The derivative of f of x3 is equal to f of x1 or 2, doesn't really matter, minus x1 over x2. So we know this, right? We have that actually from up here when we do the mean value theorem, right? Because this is what it means. So all of this is true, which means this piece is true, right? So that's the piece we're using. So what does that mean? So let's consider, hence, f of x, the derivative of x is equal to 2ax plus b. That's fair. We know that. So now, what are we doing? Well, this is really some calculation, but let's put it together. So this is 2 a x 3 plus b plus b is equal to ax2 squared plus b x2 plus c minus ax1 squared plus b1 plus c. And that is over 2. X2. Ooh. Oh, I didn't know I could do that. No, I'm stuck, aren't I? Dang it. Come on. 2 minus x1. All right. What does that equal? Well, the c's are going to cancel because this is a positive c here. Here is a negative c, right? Because the negative is going to distribute. So c's are going to cancel. I'm going to be left with a times 2 squared minus 1 squared plus b times x2 minus x1 over x2 minus x1. Okay, well, but now I have, in this term, I have an x2 minus x1, and in this term I do. So I can see some factoring that might need to be done, but I have to distribute this, right? Because this is going to be, this is x squared, x2 squared. So I'm going to pull one of those out, one of these out. So you could think of it as distributing this through and then pulling one out, but this is going to factor, and it's going to be left with x2 minus x1 times, and now we'll just distribute through with the pieces. So what are we going to be left with? Well, we're going to be left with a b, but on this side, I'm going to be left with a times each one of those. So I'm going to have ax2 plus ax1 plus b over x2 minus x1. Well, this, let's do that in color. This is going to filter right there. That's 1. So I'm left with just what's up top. And we have to figure out how this distributes through. Okay, I may not have enough on this page, but I'm practically done, so I feel like I should. Let's go ahead and add a page. Come on. Do I want to keep? Yeah. Let's add a page right there. Let's go and we'll do a blank one. And I'm going to keep working from where I'm at. I'm not going to rewrite it. I'm going to rewrite where we were, just so everything's clear. So what do we have? We have 2, dang it. I have 2ax cubed, or not x cubed, x3 plus b, and it's equal to, what did we have left? We had an ax squared, or no, x sub 2, plus an ax sub 1, plus a b. plus a b. Well, if I minus b from both sides, that's going to filter off. That's a nice, easy filter. Let's filter that off. Okay. Well, maybe I should take out the a's. That might make things look a little better. Let's do that. So now I have 2ax 3 is equal to a times squared plus x1. Now I can divide by a to filter my a's off. So divide by a, right? They're gone. Okay. What do I have left with? I have 2x3 is equal to x2 plus x1, divide by 2, divide by 2. Now I have that x3 is equal to x2 plus x1 over 2. Which is, so let's be clear, this is the midpoint of x1, the closed interval x1, x2, right? Maybe put a box there. We just showed it. The proof. I don't remember. I don't remember what it was asking, but that is the midpoint. That's what it was asking for. We're going to go back and look at it just because I don't remember if it was actually a proof or not. Let's see. Suppose that, show. Yep, you're kind of proving when it says show. So putting the box is fine. We're showing that for any x1 and x2, the unique value of x3 that satisfies the mean value theorem is the midpoint, which we just did. Success. What's the next question? Let's see if we get through. Spleens. You guys can read these. I don't feel like these are, I mean, are they necessary? No, but this can help when you're finding a quadratic with 3 points. So you're trying to figure out what the quadratic is. If you have 3 variables, then you need a system of equations with 3 equations. So this might come in handy. This is using this idea of a splinter to kind of fine tune. We know the points, then we start putting stuff together. And it's good for figuring out what your graph might look like and cleaning them up. In the beginning, they don't look very clean, but you gradually take steps and clean them. So let's use this example. The quadratic polynomial standard ax squared plus bx plus c, and we want to find that through a particular point. Okay, so we want to say, okay, at when x is 1, it's equal to 9. When x is negative 2, it's equal to 27. And when x is 4, it's equal to 3. So we need a system of 3 equations. Let's be clear that the pieces we're looking for are the A, B, and C. Okay, so my first thought is I'm going to say, well, what is it at 1, 9? Okay, what is it at 1, 9? So at 1, 9, it is 9 is equal to A times 1 squared plus B times 1 plus C. Well, this is going to be 9 is equal to A plus B plus C. Great. All right. And at negative 2, 27. What is it? All right. So that means that 27 equal to A times -2 squared plus B times -2 plus C. So that means 27 is equal to, that's going to be 4A minus 2B plus C. Okay. And then at, what are we at? 4, 3, 4, comma 3. 4, comma 3. So that would mean we have 3 is equal to A 4 squared plus B 4 plus C. All right, so 3 is equal to 16A plus 4B plus C. Okay, and then what are my choices? So I could use any system of equations properties that I would like. So I could do this using addition or elimination, whatever you guys want to call it. I could use substitution or, yeah, there's 3. I'm going to use linear algebra just because that is effectively simpler. What would I have? I would have something that looks like this. A, B, C, 9, and this is really me taking this equation, right? And this equation, 4A minus 2B plus C equal to 27, and taking this equation, 16A plus 4B plus C is equal to 3. And I'm going to put it in a matrix. So this matrix would look something like, what would this one be? This would be kind of messy, but it would be, actually, it's not that messy. It's 1, 1, 1, 9, and then we have 4, -2, 1, 27, and then we have 16, 4, 1, 3. And I would go through the solving process. And to be honest, like I tend to not rely on technology. So like my first action might be row. And this doesn't have to be your first action, right? Like there's choices when we do matrices. -4 row 1 plus row 2. All right, I might do this. That might be my first action, right? And then I end up with a new matrix. That's kind of the way this works. I would have, put down what we'd have, right? So 1 didn't change. 1, 1, 1, row 1, I'm sorry. That's when I said that. What did change? Row 2 changed. Row 2 now becomes 0, -6, -3, and -9. All beautiful numbers. Row 4, I didn't change, or row 3, I didn't change. So this stays 16, 4, 1, 3. Great. But my leading terms are 1, and I have a 0. So now I need to get this one down to 0. So I might do, what would I do? I would do row 3. The new row 3 is going to equal -16 row 1 added to row 3. That would be a nice, easy one. What is this going to give me? My row 1 isn't changing. 1, 1, 1, 9. My row 2 isn't changing. There's actually some kind of like calming sensation of doing this that I always enjoy. So this becomes 0. 16, 4, that's going to be negative 12. And then that's going to be negative 15. And okay, 16 times 9. That's going to be negative 141. Beautiful. Look at that. Look at that. Our first term is already set up. It's looking pretty good. Of course, we got to keep going. We're not done. So what might we do? Well, a couple of options. I want this negative 6 to be, I want that to be a 1. So I'm just going to do this. Nice, easy. I'm not going to go through all these, just so you know. How many steps did I take when I did it? I did it by hand to get there. So 1, 2, 3, 4, 7, 8. I took 8 steps, and we've done 1, 2. All right, so maybe I'll do this third one, and then I'll let you do the other 5. R2. Yeah, let's do this. R2 is going to equal, because we can only multiply and divide, and we can add rows together, but I can't just add a number to stuff. So let's just multiply by 1/6. It could bite me. This could, I mean, it's going to be fractional anyway. I know the results will be fractional, so that doesn't bother me. Let's do that one. So what happens? So row 1 stays the same. 1, 1, 1, 9. Row 1 stays the same. Row 2, well, negative 1/6 times 0 is still 0. Nothing changed. Isn't that beautiful? Let's see. This becomes a 1. That's great. Negative over negative, positive, that's a half. That's beautiful. And then what do we have? We have 9 over 3 half. Oh, negative 3. Nope, wait. Hold on, watch my signs. It was negative, it's negative, that's positive. 3 halves. 3 halves. That's not bad. I didn't do anything to the other one, so let's go ahead and just write that in. What do we have? We have 0, negative 12, negative 15, and then we have negative 1, 4, 1. Okay. Beautiful. Okay, so what then you kind of keep going through this process. Like I might, maybe at this point I want to clear this value right there. Maybe I want to clear that, right? I might do R1 is going to equal negative R2 plus R1. Yeah, I could have wrote that as R1 minus R2. Choice doesn't really matter. Why'd I do that? Well, one, because the negative 0 added to that isn't going to change anything. So now my new row 1 becomes 1, 0. That's going to be negative, so that's going to be a positive half. 9. Ooh, 9. Negative 3 halves. Okay, so that's going to be 15 halves. 2 is going to stay the same. 0, 1, 1 half. 3 halves. 3 halves. 3 I didn't touch. Negative 12. Negative 15. And then negative the big one, 4. And then, oh, lots of choices, but I'm going to do R3 is going to equal 12 R2 plus R3, right? That would be totally fine. So this would be 1's not changing again. So I was going to stop, huh? Okay, well let's just finish this. So 1, we'll finish this piece. 1 half, and then 15 halves. 2 is not changing, so 0, 1 half, 3 halves. And then what do we get here? So we're going to get 0. That was the goal. We're going to get 0. That's beautiful. 12 times R2. That's going to be 6. And then negative is going to be negative 9. And then this is going to be, yeah, it's going to be 6 times 3 is 18. So this is going to be negative 123. Okay. Great. Okay. You're going to keep going, right? You're going to keep going and you're going to find some values. And I'll give you what you should find. I've pretty much set you up. This is 1, 2, 3, 4. We've done 4 steps, so we've done half the steps necessary. So I will give you what you should get, what makes sense, or what these values work like. So you should have that A is equal to 2/3. Should get B is equal to, remember, you have to show your work. So I don't mind giving you these negative 16 thirds, and C should equal 41 thirds. Okay. Let's see what else there is. All right, so you guys have that. You guys can keep going. Oh yeah. Okay, so this is useful. It is interesting. Yeah. I'm not reading everything. You guys can read the slides. I'm more or less doing this to help you. Let's get to where we're working through the problems. So we have 2 circles. Oh no, you do not have 2 circles centered at the origin. What do you have? Yeah. Goes through some calculus ideas, equate the 2 slopes. Here we go. So one may, no, this isn't the 2 circle one. I thought there was a 2 circle one. Oh no, that's over there. Okay, so let's consider this one. What is this saying? This is saying one may think of that in order for a line L to be tangent to a curve at a point P, there must be some neighborhood of P in which the only intersection of L and C occurs at P. We show it's false if you consider this piecewise curve. We're choosing to set x equal to 0 on this curve because it's 1 over x in the argument. Okay. Oh, and the line. So we have 2 things. Show that it's false if we're considering, okay, so we're considering this function here and this function here. Okay. So I could think of this as what do these functions look like? And that's useful. Let's see what we're talking about. Show that the graph f and g are tangent at x equals 0. And we can use the tangency definition given in exercise 1. And you'll need to use the definition of a derivative to compute f prime of 0. Okay. So, all right, right off the bat, I see that at 0, right? So at, come on, stop that. At x equals 0, f of x equals 0. And, right, I know this to be true. I also know g of x is equal to 0, right? 1 in this equation the slope is always zero, right? This one, the slope's always zero, so that's not even that interesting. So I have to use the definition of a derivative. Okay. All right, I can do that. So what is the definition of a derivative? The derivative says that for this case, right, let's consider what's happening at this case. It says that, um, let's maybe write it over here. In this case, it says that f prime of zero, that's the derivative we're using. This is the limit as h approaches zero of this function f of 0 plus h, right, minus f of 0, okay, over h. Okay. Well, let's consider what this says. We know the value of f of 0. It's 0. So this piece is 0. This piece there is 0. 0 plus h is just f of h. So this actually becomes what? It becomes f of h. Come on, f of h minus 0. Minus 0 over h. Or essentially, and it's a limit still, right? Like I'm not writing that. You guys should write that. So this becomes the limit as h approaches 0. Well, let's plug in h into this, right? Into this whole thing. So h squared sine of 1 over h all over h, right? So f of h is this, is f of h is the top, this h is the bottom. Well, this is going to, let's do that in a different color. This is going to filter off one of those. So this actually equals, right, h sine of 1 over h. Okay. And this is the limit of as h approaches 0, which we're trying to show should equal 0. Yep. Okay. So this equals 0. Remember, it's the limit as h approaches 0. So as this thing becomes 0, the whole thing does. Okay. So that equals 0. Because the slope here is always 0, g of the derivative of g of x is always going to equal 0. So now we have thus the derivative of f of 0 equals the derivative of g of 0 at x equals 0. And since their derivatives are the same at that location, therefore, f of x and g of x are tangent at x equals 0. Since they have the same slopes, right? So you may want to put that since, but I mean, essentially, if they have the derivative at the same place, they have the same slope at the same place because the derivative is slope. Now, this next piece says, show that in any open interval containing x equals 0, there exists a t that is not 0, where the f of t and g of t is equal to 0. And, excuse me. So we want to consider an open interval. It doesn't really matter what open interval. Let me switch colors again. Okay. So this is, part B. That actually was part A, right? So we get that, though not quite in that order, right? We started here, and then we went over here, and then we went back here. So just utilizing the space on the slide as best I can. You guys can pause it and go slower. So let's consider consider an open interval. Let's consider just a random open interval. We're not going to use numbers because, who likes to work with numbers? Jeez. We're math people. The interval negative a comma a. That's a nice open interval, right? That's a perfect open interval. Then let's see, show that at any open interval, there's any open interval, that's why I used A, containing x equals 0, because negative to positive means there is going to be a 0 in there. Then for this to happen, f of t, right, some t that's in that interval, to equal g of t, we would have t squared sine of 1 over t is equal to 0. Okay, well, the trivial case is t equals 0, but we are not allowed to use that one. So we're going to take the case. We don't even have to prove the trivial case because we're told not to use it. Take the case where t doesn't equal 0, right? Okay. So because this gave us either t squared equals 0, which we don't want to use, or sine of 1 over t is equal to 0, which that we do want to use. So knowing this, we could say hence, sine of 1 over t is equal to 0, and because we know our trig and we understand that, that means 1 over t is equal to some number times pi, right? Where n is an integer, right? So we should be clear. Where an element of v, right? All right, so n is an integer. So we need to find out what t is, right? Because that's the objective of this, is what is t. So consider that using this logic, it means t must equal 1 over n pi. This means, what does this mean? This means, put a period there. T could be got that right, nice squiggly line, negative 1 over 2 pi, could be negative 1 over pi, right, could be 1 over pi, could be 1 over 2 pi, and dot, 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 the ellipse, right? And then squiggly, could be any of those, right? So that's what we've shown. So we might say something like, thus there are values, many of them, values of t other than t equals 0, such that f of t equals g of t. Remember, g of t is 0, always equals 0. And we might be real formal. If we wanted to be real formal, we might say, because it did say show, right? So this is kind of a proof, and we've kind of done this. Again, it's not a real formal proof. We can say in any open interval containing or including x equals 0, there exists a t not equal to 0 with equal to 0. There we go. Next, let's see. You don't have to do this. Yeah, you don't have to do this. If you want to do this, what are you finding? So if you want to, again, you don't have to. We have two circles. One's bigger than the other. We have a tangent line that goes crap. Tangent line, pretend it hits my circle here, okay? And it goes this way through there, right? That's the idea. This point is often labeled as T. We also have this tangent. Let's change the color. And this one, and this point, come on, where we intersect is labeled D. Okay. And again, you don't have to do this, but this would use the idea that, oops, change back to the other color. T is R1 x2 plus R2 1 over R1 plus R2. That's the x value, and then the y value is R1 y y2 plus R2 y1 over R1 plus R2. Those are those points. And then that should give you those. What do you do? You can talk about the tangent line through T, and to do that, you would do y minus 0 is equal to plus minus 3 over the square root of 40 x minus 1/3. You'll know where these two come from right there after you solve for t. This would be the two tangents. There's a plus minus. You're going to get both of them. You're going to solve these for y. That's kind of the idea. And then for d, D is going to use the same idea, R1x2 minus R2 x1 over R1 minus R2, right? It's going to use that. Tangent to the circle, okay. And then, well, okay. Both of these circles have a y value centered on, right? There's nothing with that. There's nothing with that. So we're clear, this is 0. Yes, you could write out the equation, but it's still going to be 0, so it doesn't really matter. And then you would use the equation for D with the tangent at T. Tangent at D is going to use this. It's going to use same idea, y minus 0. Again, that's still silly, but right now, and then you're going to have what's this one going to be? This one's going to be 1 over 4. 3. Yeah, 4 square root of 3, and it's going to be x. This one's going to be actually plus 9. Again, these two come from your D, that comes from your T. So you can do it. You can get the 4 lines tangent to this, but you do not have to do. Okay. All right. I think that's good. I'm going to go ahead and stop sharing. I hope you can hear this okay. That is genuinely my hope, because I do know this has been challenging. At least it's not sounding very loud. Stop recording.